I'm Paul Olson. I'm professor of Earth and Environmental Sciences at Columbia University in the city of New York.
I am Yujing Wu. I'm a new postdoc here at Paris Observatory. I'm a geologist, and now I work with Professor Jacques Lascar. My study is related to cyclostratigraphy.
I'm Steve Hesselboe, and I'm Professor of Geology at the University of Exeter. I'm working on the early Jurassic timescale and trying to refine the timescale so we can understand the rate at which Earth processes.
I'm Baptiste Loire. I'm a PhD student here in Paris Observatory, and I'm working on oceanic tides.
My name is Margriet. I'm a postdoctoral researcher in Madison, Wisconsin, in the US. And I'm part of the AstroGeo group. So I'm a geologist and I'm a cyclostratigrapher. And I mostly go into the field to explore new archives of astronomically induced climate change.
Michael Gattino. In the AstroGeo project, I am the developer of a numerical integrator for the planetary evolution. I work also on the background of AstroGeo tools.
I'm Elias Pitavi, software engineer at the IMCC, funded by the AstroGeo project.
My name is Bianca. I'm a PhD student at Utrecht University, and I'm supervised by Frits Hulge. My project is about astronomical forcing in the Ediacaran-Nama group.
I am Gwenaël Boué. I am a lecturer at Sorbonne Université and working at the Observatory of Paris at the IMCCE. My research is on the rotational dynamics of celestial bodies and tidal deformations.
I'm Yan Nanfang from Nanjing Institute of Geology and Paleontology, Chinese Academic of Sciences. My major is sedimentology and stratigraphy. And recently I did a lot of work on the late Triassic to early Jurassic cyclostratigraphy.
My name is Frits Hulgen and I'm enjoying my visit to Paris, to the Observatoire. I'm from Utrecht University and I'm a paleoclimatologist and stratigrapher. And we have this meeting of AstroGeo here in Paris, and we are enjoying our time with a lot of discussions between the geologists and the astronomers, which is very fruitful.
I'm Naihua Xue, come from Virginia University, Brussels. I'm working on the cyclostratigraphy and astrochronology of the Ediacaran, and also I do some work for the oceanic anoxic events in Mesozoic.
I'm Mohammed. I'm a postdoc at the Observatory in Paris at the moment. And I'm interested and I work on planetary science in general, and I study the evolution of planetary systems with a focus on the Earth-Moon system in specific. And I'm within this AstroGeo team, which is quite a rich interdisciplinary team between planetary science, astronomy of the solar system, and geology of the Earth, combining all kinds of data, simulations, theory, from all ends between geology, geophysics, and astronomy.
We solve the Laplace tidal equations, which are simplified free dynamic equations for tidal waves, in which we have some key ingredients. First ingredient, Coriolis, which is maybe the main source of complexity.
So one option is that the sedimentation rate was became double, right? So you see here the thickness of the layers becomes approximately like double of that. But another explanation is that this is a very long eccentricity node. So you have a long interval where there's muted eccentricity and obliquity starts to dominate, and you get this characteristic obliquity precession interference patterns again, but obliquity is dominating.
And today we are shooting on the moon by using the lunar laser ranging. And the principle is to measure the round-trip time of a photon emitted from an Earth station that go to the moon. Here is the retroreflector, that is a mirror-like, and the photons go exactly in the same direction.
The rocks we'll talk about now come from the Newark Rift Basin near New York City. And just to show you what these look like, this is continuous core that was collected in the Newark Basin at 7 different core holes, which had about 25% overlap stratigraphically in the early 1990s. And there's 6,700 meters of continuous core. It's one of the longest records of core available in the world. And this is what it looks like. So the white things you see, these parabolas, are fractures. They have very little to do with sedimentation. So
my field is, let's say, psychostratigraphy. So we are looking at the regular alternations in the sediments, in the rocks that we see that have been deposited in the sea and in the lakes. And we try to understand, let's say, the influence of climate, and then especially what we call this astronomical climate forcing. So the changes in climate that are the result of changes in the insolation caused by Earth's orbital parameters.
I reconstruct the axial precession frequency in the past, and this parameter, this axial precession frequency, it is important in the application of astrochronology. Now we have some models on this parameter, but we need more geological data to constrain this parameter in the past.
I think the format is really very nice. So we have a lot of time to discuss during the presentations and between the presentations, and particularly the format of having completely free sessions in the afternoon where issues that come up in the morning can be expanded upon and really discussed in great detail. That's been particularly productive, I think. And the other advantage of the meeting is, of course, having a field trip in the middle as well. I'm hoping and expecting that will lead to other fortuitous discussions that you wouldn't otherwise plan for.
All sand, the white sand, has been bleached. Originally, the deposit contained organic matter. A lot of life was in the basin where it was deposited, in the marine basin, on beaches. And if you look on sand pits, there is never any fracture in the sandstone pans. So the fracture developed only on the outcrop.
So this organization of the faucets might point to tidal influence.
I was thinking sort of megaliths.
So we will just make a small walk through the boulders to come up top and see how the landscape is evolving recently, how the rocks are weathering.
I think the workshop is very, very good especially for geologists and young people to know more about the astronomical knowledge.
It's interesting to learn about the geology part and how they try to find astronomical signature in their data.
I realize this project is a very multidisciplinary project, and in this meeting I met researchers from various research backgrounds who are astronomers and computer scientists and like me, geologists.
I think the meeting has really been very stimulating. It's always great, hard work to be at a meeting that is so interdisciplinary, so that you're exposed all the time, both to ideas and methods that you're not familiar with.
The meeting so far has really given me an excellent sense of really sophisticated views in my my perspective, of how geological data can be used to constrain the way the Earth dynamically interacts with its components in terms of tides and plate positions and so forth, to then influence the rotation rate of the Earth and the recession of the Moon from the Earth in geological time.
It's very nice to see that how over the years a lot of things come out. So in the science way. So we started with all these problems, and then somehow if you bring astronomers and geologists together, and you explain to each other the problems and the different approaches, like within a couple of years, suddenly some of the issues have been solved.
My first meeting of AstroGeo was really difficult because it was the first time actually that I, as an astrophysicist, especially in theory, listening to geologists with a lot of different tools and language that we're using. So it was quite difficult, but now I think with this third meeting and 3 years of interactions with fellow geologists and cyclostratigraphers, stratigraphers, I think I've acquired a sufficient basis of the tools and the skill set that they use. In this meeting specifically, I'm learning a lot about dating, about tuning. I think we've achieved a lot. We have a lot to work on. It's very exciting. We've created a lot of tools, but I think the challenge now is to combine all these tools in a coherent manner.